Welcome back once again. This is Lecture 10, Part 2, second half of 4.2, Classifying Chemical Changes and Predicting Products. I was filming this a bit ago. My mic went out again in the middle, and I couldn't bear to have this be broken up into 3 parts. So I'm giving it a go again. Hopefully it works this time. Just want to remind everybody that what we learned about in Part 1 was that there are 3 types of reactions so far we've seen. Those are synthesis, where there's just one product. There's decomposition, where there's just one reactant. And then there's combustion, where that's an organic compound, either a hydrocarbon or a carbohydrate, although we did see an alcohol, reacting with oxygen to form carbon dioxide gas and water. We're going to look at the latter 3 types of reactions today: single replacement, double replacement, and then that special type of double replacement called a neutralization reaction. Before we get into these new types of reactions, I thought it would be a good idea to give you a chance to review and practice what you learned from Part 1. So take a moment, if you're willing, to do this practice problem at the top of page 178. I'm on 178 of the ebook. And then pause your video, come back in a moment when you're done, and see how you did. The first one is decomposition. There's just one reactant. It's iron 3 oxide. It's a binary compound, so it'll decompose into its 2 component elements, iron and oxygen. Oxygen, remember, is diatomic. Next one is combustion. It's actually an alcohol as opposed to a carbohydrate, but you could imagine it's a carbohydrate reacting with oxygen to form carbon dioxide and water. That was a little bit tricky for me to balance. When I got to oxygens, I realized that there wasn't a whole number I could use as a coefficient. So I temporarily put a 4.5 there, which balanced it, but I can't have a half a coefficient, so I just doubled everything and then got 2, 9, 6, and 8. So that's a little trick, is you can temporarily put a half a coefficient if that balances everything, and then double it. 3 is synthesis. This is a metal oxide and water. You might have thought it was a double replacement because earlier you heard that 2 compounds can be a double replacement, but that's only if they're ionic, and water is not. So this is a synthesis, and it is forming a base whose anion is hydroxide, or we could also say it's forming a metal hydroxide. So it's silver hydroxide that is the product. And then in 4, with a single reactant, we know it's decomposition, and this is a base or a metal hydroxide, and that decomposes into a metal oxide and water. 3 and 4 are similar to each other, but in a way backward. So we'll now start looking at the first of 3 types of reactions that Part 2 will address: single replacement and then double replacement. And within that conversation about double replacement, we'll talk about neutralization reactions. I'm on page 178 of the ebook, and I'll read to you this section at the top. A single replacement reaction, or sometimes referred to as single displacement, involves a reaction between a compound and an element, so that the element replaces an element of the same type in the compound and a new element. That element by itself can either be a metal or a nonmetal. So if the element that's by itself is a metal, it will replace the metal in the compound and form a bond with the nonmetal that was there. And if the element that's by itself is a nonmetal, it will replace the nonmetal in the compound, forming a bond or a compound with the metal that was originally in the compound. And that's what it says down here, is that during a single replacement reaction, a free, uncombined element kicks out a combined element and takes its place. Metals will always bond with nonmetals. So when the metal kicks out the metal in the compound, it will bond with the nonmetal that remains, and vice versa is true as well. Active metals, it says in red here, may also replace hydrogen. Hydrogen, as a cation, acts like a metal. It's positively charged, like metal ions are. So if you see hydrogen out front, which will happen in an acid or in water sometimes, then the metal that's by itself, if the reaction occurs, we'll learn that these don't always occur. If the reaction occurs, that metal by itself will replace hydrogen in either acid or in water. And then that hydrogen that's by itself forms hydrogen gas, H2 gas. So we see those 3 different examples depicted below. These are all single replacement reactions. If the element by itself is a metal, in this case potassium, and the reaction occurs, again we'll come back to that in a bit, then it would replace the metal in the compound, copper, forming a compound with nitrate. And we see that over here. Potassium is now with nitrate, and copper is now by itself. In this next one, we see a metal sodium reacting with HOH. That's actually water. But if we think of water as HOH instead of H2O, and think of the one hydrogen as being a cation in water, this can then be a single replacement reaction where sodium replaces the hydrogen cation in water, forming sodium hydroxide and hydrogen gas. And then lastly, we see the element by itself being a nonmetal. Bromine in this case is reacting with sodium iodide. It would replace the nonmetal in the compound, iodine, forming a bond with sodium. So we see sodium bromide and iodine as products. And iodine, again, is diatomic. This highlight in yellow is mentioning what I did a moment ago, which is to notice that when hydrogen is being replaced in water, to think of water's formula as HOH, as the hydrogen cation and hydroxide anion, which makes it evident that the product will be a hydroxide, that hydroxide will remain when hydrogen gets kicked out. In blue here, and this is the bit about whether or not reactions actually occur, it tells us that to determine whether a single replacement reaction will occur or not, we need to compare the chemical reactivity of the element that's by itself to the element that it would potentially replace in the compound. And when we flip our page, we'll see table 422 that ranks metals and nonmetals according to their reactivity. Reactivity is the tendency of a substance to undergo a chemical change. If we imagine that the element by itself is neutral, that it hasn't undergone a chemical change yet, and that the elements that are in the compound, the ions that are in the compound, have undergone a chemical change to be in that compound, that if the element by itself is more reactive than the ion, a reaction will occur, because then that element that's by itself ends up being the ion and having reacted. If, on the other hand, the element that's by itself is less reactive than the than the ion in the compound, a reaction won't occur. I've flipped my page. I'm on 179 now of the ebook, and this is that table I just referred to about activity or reactivity. Metals are on the left, nonmetals are on the right. This only has the halogens, those in group 7, and the higher up an element is, the more reactive it is. So we can see that of those metals listed, lithium is the most reactive, and we get into our section about periodic trends. We'll learn why, but lithium is more reactive than potassium, and on down the line. Fluorine is the most reactive nonmetal or halogen, followed by chlorine, bromine, and iodine, for reasons, again, we'll learn later. And take a look at how hydrogen has an asterisk. It's an important asterisk to pay attention to. Hydrogen, it says down below, may be displaced from most acids by all metals above it. So if the hydrogen that's in the compound is as an acid and not water, then this activity series works just as it is. For example, tin would replace hydrogen in an acid, so would lead, but copper wouldn't. If, though, the hydrogen is in water, not in an acid, but H2O, then only metals above magnesium would replace the hydrogen in water. So aluminum, if it reacts with water, doesn't react, which is probably good. We make a lot of things out of aluminum. But if sodium is added to water, there will be a reaction. So again, only metals above magnesium will react with hydrogen when it's in water, whereas every element, or metal, above hydrogen will react with it when it's an acid. I recommend you give this quick check a go to try to do it on your own first, using the information you were just given, and then come back to the video in a moment once you're done and see how you did. I found that one would be a reaction. The metal sodium, which, if the reaction occurs, would replace aluminum, is higher up than aluminum on the activity series, meaning it's more likely to lose its valence electrons and end up being an ion. In fact, it gives its valence electrons to aluminum, rendering aluminum neutral and sodium an ion. And that one's balanced for you. I found that 2 is not a reaction. Copper, which is a metal, is not more reactive than the metal ion potassium. It's below it on the activity series, so there's no reaction there. And notice I wrote NR for no reaction. 3, I did find is a reaction. Fluorine, which is a nonmetal, I compared to iodine's reactivity. And because fluorine is above iodine on the activity series, it will replace it, forming a bond with the metal ion lithium and giving us iodine. And iodine is diatomic. This 4th one down is calcium reacting with water, written as HOH. You'd more likely see it as H2O, but give you a little hint here to think of water as HOH. And again, when we're dealing with water, the metal by itself, in this case calcium, will only replace the hydrogen if it's above magnesium. And calcium is, therefore calcium will bond with hydroxide, and hydrogen, always being diatomic, is written as H2. I have flipped my page. I'm now on 180 of the ebook, and we're looking at this section titled Double Replacement Reactions. A double replacement reaction is a chemical reaction between two compounds. They will both be ionic that trade cations. We picture the cations trading places. We could picture the anions trading places. The same thing would happen, but I just picture the cations trading places. It's important to remember that an ionic compound is made up of a positively charged ion called a cation and a negatively charged ion called an anion. And when these ions trade positions, a new set of compounds is formed. Double replacement reactions tend almost always to occur in an aqueous environment. And like we learned earlier, when an ionic compound is dissolved in water, the ions dissociate from each other and are free to move around. So we really need to think of, if we go down here to this double replacement reaction, sodium chloride and silver nitrate reacting, we really need to think of this as sodium ions dissolved in water along with chloride ions, along with silver ions and nitrate ions. It's really just an even mixture of four types of ions. But in the presence of each other, those ions can recombine in new ways. And if two of the ions, when they're in the same environment together, when they're in water together, are more attracted to each other than they are to water, if these two ions form what's called an insoluble compound, because again, they're more attracted to each other than they are to water, they will precipitate out of solution. That's what drives many, not all, double replacement reactions to occur, is that when these four ions are in solution together, if two of those ions are insoluble, more attracted to each other than water, they'll drop out of solution, creating this new compound, leaving the other two ions behind. And we see that here, with sodium chloride reacting with silver nitrate, forming insoluble or solid silver chloride, a silver chloride precipitate, and sodium nitrate. Our book says that predicting which salt will precipitate and drive the double replacement reaction requires information about the relative solubilities of the products. Later on, we will look at a table that has what's called solubility rules on it that tell us, given the combination of ions, what salts are soluble and not, and learn a little bit of the chemistry behind why. For now, though, if you remember two rules, two solubility rules, you'll be able to predict all of the double replacement reactions that you'll see. If a salt, if an ionic compound has a group 1 metal in it, an alkali metal, sodium, potassium, rubidium, cesium, those are always soluble. Any salt with a group 1 metal in it is soluble, which is why sodium chloride with a group 1 metal in it is soluble, or sodium nitrate, for example. The other rule to remember right now is that all nitrates are soluble. Any salt that has NO3 in it is soluble, which is why silver nitrate and sodium nitrate is soluble. It's also soluble because sodium is a group 1 metal. Assume that for now all double replacement reactions will occur, that they will occur, and that one of the products will be insoluble and one will be soluble. And you'll be able to use those solubility rules, all group 1 metal salts are soluble, all nitrates are soluble, to predict which of the salts, which of the products is going to be solid, is going to be the precipitate, and which of them will remain in solution. Let's practice that before we get to the second half of this section about neutralization reactions. I've flipped to the next page. I'm on 181 of the ebook now, and I'm looking at practice problem 3 on page 181 of the ebook. This is a double replacement reaction because these are two compounds and they're both ionic compounds. Ammonium sulfide and cesium hydroxide are both ionic compounds. Cesium hydroxide is a base, by the way, but this isn't a neutralization reaction because ammonium sulfide is not an acid. So this is just a double replacement reaction. So we picture the cation switching places, we picture ammonium and cesium switching places, and in a moment you'll see me having written cesium paired with sulfide as one product, and ammonium being paired with hydroxide as another product. And there we have it, ammonium and cesium having switched places, forming ammonium hydroxide and cesium sulfide. A bit ago you heard me say assume these all occur, and that if and when they occur, one of the products is going to be solid, the precipitate, and the other one will be soluble. So we're going to use our solubility rules to figure out which one will be soluble. Remember, all group 1 metal salts or nitrates are soluble, and since cesium is a group 1 metal salt, this would be the soluble product, and this would be the precipitate. And I didn't balance it. I'm just not going to. But this one's actually a little bit trickier than it might seem. So I'm going to go back to the prior page, teach you a couple more things, and then we'll come back to this and fix it to be right. So I'm now on 180 of the ebook, looking at this section that's highlighted here. This tells us that a few products of double replacement reactions are not very stable and will spontaneously decompose to form water and a gas. The two to pay attention to in this class, the two to remember, are carbonic acid, H2CO3, we'll see it in a moment, that whenever it forms, decomposes immediately into CO2 and H2O. So if you ever were to want to write H2CO3 as a product, know that you really shouldn't. You should immediately write it as CO2 and H2O. If you want to write it as H2CO3 first, and then transform it underneath to H2O and CO2, you can. It's this one, though, that we just saw being produced. Ammonium hydroxide, NH4OH, is very unstable and will decompose almost instantly into ammonia gas, NH3 gas, and water. So we're going to go back to the page we were just on and change ammonium hydroxide to ammonia gas and water. So it's this here that we can't write as a solid. Now, we thought it was a moment ago because I told you that one product will be aqueous and one won't. And while that's normally true, in this case, we've got to get rid of NH4OH and write H2O and NH. And there we go. So as it turns out, the reason this one occurs isn't in fact because one of the products was soluble and one wasn't, but rather because one of the products is soluble and the other two are a gas and a liquid and also leave the system as a result of that. And here on the prior page, I've flipped back again, we see that same thing happening. Instead of ammonium hydroxide being written, we see water, liquid water, and ammonia gas, and then the soluble sodium bromide. Above, double replacement reaction, potassium would be switching places with hydrogen, forming potassium chloride, and then hydrogen will pair with CO3 to form carbonic acid. Now, this is a case where carbonic acid, being unstable, immediately decomposes into water and carbon dioxide, which is why we see H2O and CO2 here instead of H2CO3. So we're going to scroll back up, talk about neutralization reactions, and that'll put us close to the end of this lecture. And here we see that a neutralization reaction always occurs between an acid and a base. These are just double replacement reactions that are subcategorized as neutralization. The products are always going to be water and a salt, and we'll see why water is one product and why salt would always be the other. So here's an example of one down here. We've got sulfuric acid reacting with potassium hydroxide. We know sulfuric acid is an acid because it has H plus as its cation, and this is a base because OH minus is the anion in strong bases. So we picture hydrogen and potassium switching places. Potassium will be in a compound with sulfate over here, and then hydrogen will pair with hydroxide to form HOH, but what should really be written as H2O, and then water is a liquid. So this is a double replacement reaction between an acid and a base called a neutralization reaction where a salt and water are formed. A salt is just another term for an ionic compound. Again, a salt is just another term for an ionic compound. Most neutralization reactions are exothermic, release energy, release heat, and so that's why we see heat here written as a product. You don't need to do that, though. Unless you're told to explicitly include the word heat in an equation, don't worry about including it. Going to solve sample problems 2 and 3 with you as the last thing we'll do in this lecture. If you want to take a moment to try these on your own, pause the video and come back and see how you did. I recommend that. Again, we're doing sample problems 2 and 3 on page 181 of your ebook. So in 2, it's a double replacement reaction. We know that because these are both ionic compounds. We picture the cation switching places. We picture lithium and calcium switching places. So that will pair lithium with nitrate and calcium with sulfite. I might have said sulfate earlier. Well, lithium and nitrate are both 1 plus and 1 minus ions respectively, so it's just going to be LiNO3. And calcium and sulfite are 2 minus and 2 plus ions, anti respectively. Ugh. So we're going to get calcium sulfite. All right, well, assuming this occurs, that means that one product is soluble and one's not, or that carbonic acid or ammonium hydroxide are made, which drives it forward for another reason, but that's not the case. So which one's soluble and which one's not? Well, if the salt contains a group 1 metal or nitrate, it's soluble. Otherwise, we assume it's not soluble. That renders lithium nitrate the soluble one for two reasons. Lithium is group 1 and nitrate's nitrate. And then that means calcium sulfite would be insoluble, because again, we assume that these occur, one product soluble, one's not for now. If we look at 3, we've got sodium carbonate and hydrobromic acid. That's a double replacement reaction. Those are both ionic compounds, because remember HBr, which is an acid, is also an ionic compound. So we're going to picture sodium and hydrogen switching places. Sodium will be with bromide, and hydrogen will be with carbonate. When hydrogen's with carbonate, it will be an acid. The cation being hydrogen renders hydrogen with carbonate an acid. It's going to be carbonic acid. So I'm going to write sodium bromide, NaBr, and then carbonic acid, H2CO3. But, oh, that's a lousy O. But I know carbonic acid immediately decomposes into water and carbon dioxide. So instead of writing H2CO3, I'm going to write H2O and CO2. And my stylus is struggling today, but that says H2O and CO2, if you didn't know. Probably not my stylus struggling, probably just me. So there we go. And notice that I've indicated that water is a liquid, which it is, carbon dioxide is a gas, which it is, and that sodium bromide, because sodium is a group 1 metal, would render sodium bromide soluble. And then when we balance it, we put a 2 in front of HBr and a 2 in front of NaBr, and everything looks great, except for my handwriting, of course. All right, that concludes Lecture 10, Part 2. Stay humble, work hard, be kind, love yourself, love others. See you soon.